Hi there, and welcome to this lecture on the evidence for the Earth's layers. In this lecture, we're going to talk about how we know what we know. We just got through talking about layers defined by both their physical properties and layers defined by their composition. However, it may have boggled your mind a bit to know that we had so much detail about the Earth's interior. And so in this lecture, we're going to talk about why. As part of this lecture, we're going to learn about seismic waves, and that part of the lecture will also be important for our earthquakes lecture as well. So it's not something we're going to discuss and then never look at again. We're actually going to be using this information later on as well. So try to pay close attention and take good notes for this part of the lecture. All right, let's go ahead and get started. Let's go to the next slide. So seismicity is basically divided into what are called body waves and surface waves. And we're going to focus primarily on the body waves for the purposes of looking at the Earth's interior. And the reason is body waves are defined as waves that go throughout the Earth's interior layers, whereas surface waves stay near the surface of the Earth. So all of these waves are actually generated at the exact same time when an earthquake starts. So basically what we call the focus of the earthquake. That's basically where the earth ruptures, breaks brittly, and waves are by energy release are emanated out from where the rock breaks. That's basically what earthquake's about. The shaking that is caused by the energy release is actually what we call an earthquake. So basically these waves that are generated as the rock is breaking during an earthquake is what we're going to focus on here. And in particular, we're actually going to look at only the waves that go through the Earth's interior as a whole. Surface waves we'll talk about later when we get to the part on earthquakes in this course. Okay, so the body waves are divided further into what are called primary waves and secondary waves, and we call them P waves and S waves for short. You'll see the seismic readout here on the slide, and you'll see a P with an arrow and an S with an arrow, and then they've labeled surface waves. This is the P is obviously going to be for the primary waves or P waves, and the S is going to be for the secondary waves or S waves, and then surface waves are separate. We're not going to discuss the surface waves so much today. Now this is a seismic readout, an actual seismic readout of the Northridge quake as recorded in College, Alaska. So it's important to realize that we can record waves at very great distances, and in fact that's how we get a magnitude reading for an earthquake as well as a location, specific location to an earthquake, because these waves can travel so far away. A seismic station that's very close to the epicenter would be of no use because it would be jostled around so much by all these interfering waves very close to the epicenter that it wouldn't actually record the information very well. So when we're getting information about an earthquake, we're actually using seismographs from very distant sources to find out what the numbers are in relation to a quake. Now the primary waves you'll see show up on the far left, and time is actually exhibited on the bottom part of the chart, the x-axis basically, and it's given in seconds there. And so as time's passing from left to right. So the needle records the P wave first is basically my point with that. The up and down motion would be along the y-axis, and that's actually the ground displacement during the quake. And it is very tiny. It's in microns, the measurement. And people in College, Alaska did not feel the Northridge quake. The wave energy was just too small. But we've got sensitive instruments that can record this information, and that's where it becomes very useful for scientists as well as getting numbers for the earthquake to the general public as a whole. Now the P wave arrives first, and why do you think that is? Why would the P wave arrive first and then the S wave arrives second? And then of course you can see the surface waves are even later than that. I'll give you a second to think about that. Why are the P waves arriving first? I talked about the waves all being generated at exactly the same time. Right when the earthquake starts, the waves are generated from the same place at the same time. So why would the P wave actually arrive in College, Alaska from Northridge, California first? Give you a second to think about that. All right, if you still want to think about it, go ahead and hit pause. Otherwise, go ahead and tell you it's because the P wave travels faster. Yes, that's right. These waves actually travel at different speeds. So these waves are going to show up at the seismograph at different times. And they just happen to be predictable speeds. It's not random. It's not like every different earthquake is going to have a different amount of speed as far as these waves are concerned. They do travel at the same time for each individual wave. So the P wave has a specific speed it travels. The S wave has its specific speed it travels. And the P wave is always faster. Now don't get confused and think the P wave is a different earthquake than the S wave. It's not. These waves were all generated at the same time. The P wave, the S wave, and the surface waves were all generated at the same time. They left the same location identically. They just travel at different speeds. So the P wave arrives first, obviously, then the S wave, and then the surface waves. Now, with that said, with all the predictability about the speed and how fast these travel and how they arrive at different locations and when they arrive at different locations, we can actually garner a distance from the earthquake to the epicenter just by knowing what we call the PS interval of the earthquake. All right, so let's go ahead and go to the next slide. So why do P waves travel faster? Well, they are what are called compressional waves. They travel, basically, if you see the slinky at the bottom left side of the screen, is showing a slinky at rest, and then the hand pushes the slinky toward the wall where the other side of the slinky is anchored. And you can see that the spring is actually compressing and expanding as it travels towards the wall. And that's a compressional type of wave because it's actually compressing and expanding the medium as it travels through. And earthquake P waves are very much the same way, and that's what's shown on the right hand side of the screen. You'll see the blocks in different sizes there. Some are stretched out, some are squished in, and that's because of the way the P wave travels through the solid earth. Much like through the slinky, it's compressing and expanding the earth as it travels through. And it's hard to imagine solid rock actually behaving that way, but that's exactly what happens. And in fact, during large earthquakes, sometimes we see the ground opening up near the epicenter. And a lot of people interpret that to be the actual fault line. That's not the fault line at all. That's the P wave coming through and actually expanding the earth right there and actually opening up a crack as a result. And incidentally, where the rocks are compressing, we'll see roads and other earth structures buckling up. And that's the compressional part of the P wave compressing the ground there and causing the earth to actually buckle in response. As we get further away from the epicenter, though, it doesn't really have that kind of effect on the earth where you're actually breaking the rock apart or crunching it together. It actually just makes the earth do compression and expansion in such a gentle way that we don't really see any cracks or anything. But anyway, you might be interested to know that these openings in the earth are not actually the fault line at all. It's actually just the reaction from the P wave coming through. All right, so some other facts you should know about the P wave is it does travel faster than the S wave, and the P wave also travels at different speeds through different mediums. So even though it's a very predictable speed for each type of wave, as it travels through a different medium, in other words, a different layer of the earth, it actually changes its speed as it does so. And even through different compositions, it actually will travel at different speeds as well. And that's a lot of the reason we understand where the layers of the Earth's boundaries of the layers are, is due to the differences in speeds of the S waves as they travel through the Earth. All right, let's go ahead and go to the next slide now. And secondary waves, also known as S waves, are transverse waves. Basically what that means is the Earth, or the medium in which the wave is traveling through, which we're dealing with the Earth obviously, is actually moving up and down. So conversely to the P wave, where we have expansion and compaction of the Earth as a wave moves through, the Earth in this case is actually just moving up and down, up and down. And if you're going to feel an earthquake and you are close enough to the epicenter, basically the P wave, you would feel like you would look around the room, unless you're right on top of the epicenter of a very large quake, you would feel it very strongly actually. But if it was a moderate to smaller quake, and you were somewhat near the epicenter of that quake, let's say you were in Walnut Creek and the epicenter was maybe 20 miles away from you or 30 miles away from you, and it was like a 4 on the Richter scale. The P wave would feel like, did I just feel an earthquake? And you'd look around the room and you'd look for like something swinging in the room, and you wouldn't be quite sure if that was an earthquake or not. And then the S wave, the secondary wave, would show up, and that would confirm, yes, I am feeling an earthquake. And then the surface waves, which we'll talk more about later, actually will usually prompt you to get under a table or get under a doorway. That's probably the best way to describe the differences in how you feel these waves. Now, of course, the bigger the magnitude of the earthquake is, the stronger your reactions are going to be to each type of wave. But it's something to think about. And because of the difference in the P wave and the S wave travel time, it's much like with lightning. You see the flash of light first, and then you count until you hear the thunder, and that tells you how far away the lightning is, because light travels faster than sound. Well, if you're sensitive enough to the P wave and S wave, you can actually do that with an earthquake as well, believe it or not. And in fact, I did so several years back. There was a 6, I think it was a 6.2 or something like that in the central part of California years ago, and I was in Sunnyvale at the time, and I actually felt the P and S wave from that quake because I was sitting very still in my living room, and I felt this little bump, and I was sensitive enough to know that was a P wave, or at least I thought it was, and so I waited for the S wave, and it took a while, and the S wave showed up, and then the room I was in was just moving about very gently, but it was moving about for quite a while, and that was the S wave, and then the surface waves coming in afterwards. And before I even looked up the earthquake, I knew it was far away. I knew it wasn't in the Bay Area, but I knew it was actually quite large. And then sure enough, I saw that it was in the central part of California. I'd actually speculated it might have been in Northern California, because we have a subduction zone area there where big earthquakes are possible, but it was actually along the San Andreas Fault in Central California. So you can do that with earthquakes so much, but as far as locating exactly where the earthquake is, you really can't do that just by feeling the S and P waves. You have to have some more information to do that. But anyway, I thought I would give you that as an analogy to help you understand how we use these waves in science. All right, so let's go ahead and go to the next slide. And this is a very generalized picture of the Earth, showing the earthquake epicenter at the North Pole. Now, before I even go further with this, earthquake epicenters are all over the planet, and usually not at the North Pole. We don't really have a fault line there. But they put it up at the North Pole for simplicity to make the diagram look, I think, really nice. But realize that at different epicenters, this same pattern will emit, but from the epicenter at a different location. So for example, you can see on the far left side of the Earth, you can see South America. We have a lot of earthquakes in South America, unfortunately, on the west coast there. And so what we would do is just shift this whole illustration 90 degrees to the left to emanate an earthquake epicenter from South America. So just to give you an idea of what they're trying to show here. Now, the P waves are in black and the F waves are in red, and the surface waves are not shown here at all. Now, as I mentioned, the P wave is a wave that actually is going through all mediums, liquids and solids, and we've already talked about the outer core being a liquid. And you'll notice it's only the black arrows that are going through that outer core. The outer core in this case is shown in a darker yellow. The light yellow is the inner solid core. And you can see that the black arrows just go through everything in as far as layers are concerned. You can see the wave actually bends as it travels through the liquid core. It bends slightly again when you go through the the outer core, I'm sorry. When the black lines are going through the outer core, they bend, and then you can notice as it goes through the inner core, it also bends again. And then as it leaves, it bends again. And that's because it's changing mediums. As the wave goes through a different medium, whether it be solid or liquid or brittle, solid, ductile, solid, liquid, ductile, solid, whatever the medium change is, it's going to bend a bit as it goes through the different boundary layers. So this is basically how we understand where all the layer boundaries sit, is by recording these P waves and their travel times and actually imaging them as they go through. Now you'll notice there is what's called a P wave shadow zone, and I'll talk about that in a moment because there's also an S wave shadow zone that's much bigger. In fact, you can see the whole south side of the planet has this big old S wave shadow zone. And that's because if you look at the red arrows now, they only travel through solid and they stop right at the liquid boundary in this particular image. It's important to realize the energy just doesn't disappear, by the way. I think they did this for simplicity as well in the diagram so it didn't look very messy. But what the waves do is refract off of the liquid and bounce back up to the surface. If they showed a lot of reflection and refraction, the image will look very messy. So they just show the red arrows stopping. And the point is basically to show that the outer core, the liquid outer core, will not receive the S waves. And that's because of the difference in the way these waves travel. The compressional waves can easily enter the liquid layer, whereas the up and down motion of the wave making the medium move up and down, it doesn't penetrate the liquid at all. And that's the reason for the difference in how these waves travel. Now the S wave shadow zone, notice, is really big, and that's because the S wave cannot penetrate the liquid outer core. So it makes this big zone of S wave where if you had a seismograph over on the southern part of the planet, we wouldn't see the S wave at all. And where the P wave shadow zone is, we wouldn't see any earthquake waves. So if there was an earthquake at the North Pole as shown, and we had a seismograph in the P wave shadow zone, which is shown on the left and also on the right, we actually wouldn't have any earthquakes recorded with seismographs in those zones because the P wave shadow zone actually overlaps the S wave shadow zone in this case. So you'll see on the right hand side they're showing these seismic readouts, these very generic ones, and you can see seismic station records no P or S waves. That's because neither the P or S wave will reach those parts of the planet for an earthquake at the North Pole. Whereas if you look at the very top seismic readout on the right, the P wave and the S wave show up as shown for the reasons we've already talked about. And then in the very south part of the planet, the South Pole and the areas surrounding the South Pole, we just get a P wave and no S wave on the seismic reading. So that tells, if somebody looks at a seismic readout, let's say they're in Antarctica and they've got a seismograph and they see an earthquake epicenter, or they see an earthquake, excuse me, on the seismograph, and it just shows a P wave, that person's going to know, oh, that earthquake was at, somewhere in the northern hemisphere probably, or, very far north of where their location is. And that's true of an earthquake. If we get an earthquake readout in the United States and there is no S wave shown, but there's a P wave shown, we would know that that earthquake happened in the S wave shadow zone on the other side of the planet, directly opposite the United States. And that, of course, happens all the time as well. All right, let's go ahead now and go to the next slide. And the reason, in part, we can image the Earth so nicely with these waves is because of the differences in speed and the difference in the way they travel through the Earth in general as far as changing their speeds are concerned. And just like we can image a baby in its mother's womb using sound waves, we can do this with the Earth, both what I just showed you with the interior as a whole, but we can actually also cause explosions near the surface of the Earth to image the subsurface. And in fact, oil and gas exploration is in part done and used to locate oil and gas reserves underground. And in fact, in the lower left-hand corner of the screen is an actual seismic readout of the Earth below, just the subsurface, not very deep, like the previous slide showed. But just to give you an idea, yes, we can cause explosions, we can cause these waves to emanate from that explosion to actually see the subsurface below. All right, let's go ahead and go to the next slide. And the layering by composition is basically done by field observations. So when we're looking at the crust in particular, we actually look at the rocks in person to see that. Now, obviously, the ocean floor rocks are a little bit more difficult to see. You can't hike to the ocean floor. And so we actually take ships out and we take what are called core samples. We take piping down and actually take samples that way, much like what the ship has. And on top of it, you see this big tall structure on top of the ship on the lower left-hand side of the screen. That piping is brought down that way through that structure. And actually we take sediment samples that way. We can actually get solid rock samples that way as well. So that would be the ocean floor drilling part of our exploration of the crust. It would seem that we would have mapped the whole ocean floor that way, and that's very far from the truth. We've done a lot of mapping using sonar of the ocean floor to see the topography of the ocean floor, and I think we've done all of that. But to actually take samples of the Earth's crust all over the ocean, there's still a lot of locations we haven't researched. We've gotten the key locations based on what we've done by sonar to see what's important to us. And there's a lot more of that going on now to understand the Earth's climate and the geologic past, because climate's become a big, important research area in the sciences because of climate change. And sediments can tell you a lot about the Earth's past climate. So there's a lot of research in ocean floor drilling in regards to the crust with that type of research. So I'm sure more and more, as more and more funds become available for understanding the climate, we'll get more mapping done of the ocean crust below. All right, let's go ahead and go to the next slide. And basically, when we look at the mantle, we're getting deeper down, and we obviously cannot drill directly down into the mantle. That's just really difficult. From the continents, it's basically going to be impossible because the continental crust is so thick. We can't drill very far down. However, you might think, oh, well, the oceanic crust is very, very thin, especially at the mid-ocean ridge. Well, can't we drill there? And the problem is the ocean is so heavy, and we have a hard time just getting down there to do observations, much less do any kind of severe drilling work down there. Even from ships. And on top of that, we're looking at a volcanic area. 70% of all our volcanism happens on the ocean floor, right at the mid-ocean ridge, a lot of it. So we still haven't gotten down into the mantle yet directly. However, the Earth process can do that for us, because in plate tectonics in particular, we have areas that are called subduction zones. And that's shown in the image here in this slide, where we have plates sliding underneath other plates, which basically is lithosphere subducting underneath other lithosphere as shown. And in that subduction process, some of the crustal rock of the subducting plate will actually scrape up onto the overriding plate as shown here. And we call that an accretionary prism. An accretionary prism is basically the marine sediments, but also the rocks of the oceanic lithosphere that's subducting. And we actually see that in the rock record in a few choice locations around the world. It's not very common to find, but when we do find it, it's got evidence of the mantle in it usually. Let's go ahead and go to the next slide. So an ophiolite sequence is what geologists refer to when we're looking at a sequence of rocks from the ocean floor that have been scraped up as part of an accretionary prism that include not only the crustal rocks but also part of the mantle as well usually. And in fact, it's very rare, and we actually have a lot of it here in California, believe it or not. It's a very unique area for a lot of different reasons, California is. But its geology is just bar none. We are surrounded by some very neat geology around here. And one of those things that we have are what's called ophiolite sequences. This area is not a subduction zone now, and I'll repeat that very sternly. It's not a subduction zone where we live at here right now. Up north it is, up by, past Redding, basically, on the coastline from Redding on up. So like in places like Eureka and Fortuna and things like that, that's a subduction zone up there. And we used to be a subduction zone down here millions and millions of years ago, but now our plate boundary is the San Andreas Fault. Completely different kind of boundary now. But the geology from the subduction zone of millions of years ago here still sits today, and we call that ophiolite sequence. And the Marin Headlands in Golden Gate National Recreation Area, just north of the Golden Gate Bridge, has some spectacular rocks. The Marin Headlands is usually a place people go to take postcard photographs of the Golden Gate Bridge, and a lot of people that go there will drive up the road and look out over the bay and over the Golden Gate to San Francisco and just take some spectacular footage of the city with the Golden Gate in the foreground. However, if those people just turned around and looked at the rocks, they would actually usually see people looking at the rocks as well. And that's because people come from all around the world to see these rocks. Literally, geologists and other geology enthusiasts from around the world will come just to see these. And if you just turn around and look, you'll see they just look unique just on face value without even knowing what they are. And the pictures on the left are two of those very famous rocks. The one on the top that's in red is old, ancient oceanic sediments. And you'll see the cartoon diagram on the top right kind of showing the layers of the ocean floor rocks and how they appear with the magma chamber that's usually at the mid-ocean ridge system. And the red rocks would match what is the sliver above the pillow basalts, basically. So it's usually very thin layer. It'll look thick to you if you're out there. It's definitely very much taller than you are. But as far as the whole sequence of rocks are concerned, it's the thinnest layer, relatively speaking. And they're very folded. You can see there's a lot. They're not horizontal like they were layered as, but there's a lot of folds and bends in them. And as you can imagine, in the subduction process, the rocks being scraped up are not going to stay very horizontal after all of that going on. So that's the reason for the way they look. And then the bottom left photo is actually what we call pillow basalts. And I showed you a picture of basalts crystallizing underwater, and they would form these pillows that I talked about. And the Marin Headlands has some ancient ones there as well. So very neat, spectacular, old ocean floor rocks. Just to give you an idea of an age, these were being formed about 100 million years ago. So like I said, very old, long time ago geology, not happening today. Again, we are not in subduction zone here today. This is very ancient geology we're looking at. And then the bottom right hand corner picture is actually not of the Marin Headlands, because unfortunately the ophiolite sequence in the Marin Headlands does not show the mantle part of the sequence. That's probably buried underground where we can't get to it by road cuts or anything like that. However, in Turkey there's some exposed peridotite, and actually there's other parts of of California that actually show the exposed peridotite as well. But I like this picture in Turkey because it shows it just very nicely. It's kind of got a greenish reddish color to it. The red is oxidation, much like the chert on the top left-hand side of the screen, the sediments, that is. And the bottom right is also got some oxidation as well, but it's also very kind of greenish. And that's the ultramafic color of peridotite, part of the mantle. So anyway, that's basically what these rocks look like, just very spectacular sequences of rocks. And one of the only places in the world that actually has this sequence of rocks is right in our backyard in the Marin Headlands. All right, let's go ahead and go to the next slide now. And then the layer for composition for the core obviously the core is very difficult to get to, and we actually think meteorite compositions really tell us what the core is all about. That's part of the story. Because we have a magnetic field around our planet that's actually quite strong, we have basically that's caused by metal that's convecting very rapidly, causing an electric field, which in turn causes a magnetic field. We know that we have a metal interior, and because meteorite compositions, in part, some of them are pure iron and nickel, we believe our interior is probably matching that composition as well. So that's where our iron nickel composition for the center of our planet is coming from. Plus, when seismic waves go through, at the speed at which the P wave goes through the core, it's very analogous to how it would go through iron. So there's a lot of different checks and balances. We don't use one line of reasoning to say, oh, that must be what it is. We have a lot of cross checks that we can do to really hone in on what the composition is of the interior. And it started with meteorite compositions, and then we look at the speed of the P wave going through and how does that work with iron, and it matches perfectly. So I mean, it's just, there's really no other choice. It has to be iron down there and nickel. All right, so that is the end of this lecture. Thank you very much. I will see you in the next one.